Hey guys, this video is to cover section 9.1. It's all of pages 1 to 10. I've got the filled out notes open as well as my graphing calculator, so you should do the same. So as discussed in the chapter, here's the big idea. First, we're switching gears from looking at, say, two independent data sets of male scores and female test scores and maybe looking for a significant difference in their means, to the idea that now I have one data set, but it's got two variables in it, like grades on a test and minutes studied, and we'd like to look for a relationship between those quantitative variables. So in order to do that, you'll see in section 9.1 that we will visualize that relationship with a scatter plot. We will quantify that relationship with a correlation coefficient. We will test for the significance of that correlation with a t-test. And lastly, we'll distinguish between correlation and causation. This should be enough info for you to do the homework that's due on Wednesday. That's this list of roughly 15 problems. And then section 9.2 is a bunch quicker. We are going to look at modeling a relationship between variables using a least squares regression line. And then the purpose of that model, after we have that equation, is to be able to plug in an x value and predict a y value. Meaning, you tell me how many minutes you scored on a test, and I'll be able to predict your test grade. And then assignment 2 is much shorter. We'll assess this chapter with a project task number 9. That task is not due next week, it's the following week. Of course, there are formulas that you will see problems in the notes worked out with these formulas, but we're going to emphasize some technology shortcuts. So I have my technology screen open. You will see us do pretty much just after the data entry, meaning the x values going into list 1, the y values into list 2. I'll be showing you the stat test lin reg and explaining this output. T-table's probably not needed since we're emphasizing the calculator shortcuts. Okay, so first objective, let's introduce you to what correlation is, some terminology like independent and dependent variables, describing correlation, and constructing scatter plots. So lots to do here in this first section. So when we look at a relationship between variables, we're going to create a set of ordered pairs. And ordered pairs, it's important. We need to know which one's x and which one's y, what the first value in the pair represents, and what the second value in the pair represents. So we're going to call x the independent or explanatory variable, y the dependent or response variable, and in that language it means that we want y to depend on x, or we want the changes in x to explain the changes in y. So in these pairs right here, I've identified x and y for you. Again, why would I ask you to do this? It's important in modeling and relationships to know what depends on what. So in each of these pairs, grades depend on hours studied, weights depend on heights, sales of a product depend on how much was spent in an advertising budget, and calories in a burger might depend on the fat grams in the burger. Now, just FYI, there could be relationships where we don't really care which one's X and which one's Y. An example might be SAT scores. So if we put your math and verbal score as an ordered pair, we might not really call one X and care which one we call X and which one we call Y, because there isn't necessarily a predictive relationship there. All right, well, on the way to describing correlation, we're going to display our data in a scatter plot. As usual, like in any algebra graph of ordered pairs, there's an x-axis that's horizontal, a y-axis that's vertical, and each ordered pair produces a point in the graph. Once that graph is displayed, one of these four things happen. So when we discuss correlation, we'd like to describe something like the one on the top left, number 1, as negative linear correlation. What does that mean? As the x variable goes up, the y variable tends to go down. In graph number 2, we'd like to call this positive linear correlation. As x goes up, y tends to go up. Graph 3, no correlation, not really any distinction here. So this could be something like math and verbal SAT scores. You might not see a relationship between those. Okay, or even heights and weights, the example on the slide above. Because if this is height being used to predict weight, well, of course, there's going to be some people who have small heights, but they are both light and heavy in weight, while some very tall people are both light and heavy in weight, producing kind of this random cloud of points. And then finally 4, there definitely is a relationship here, but this chapter is only about measuring correlation, and correlation will only measure linear associations, so we're going to call that one nonlinear. So a real-world example of constructing a scatter plot here at the bottom of page 4. This example will be used throughout this entire set of Chapter 9 notes. The x variable is a country's GDP, and the y variable is a country's CO2 emissions. After we graph the data, if we describe what we see, we'd call it positive linear correlation, because we see as GDP goes up, the CO2 emissions tend to go up as well. Okay, next page. Well, how do we quantify how strongly correlated two variables are? Well, luckily in stats we have a measure known as the correlation coefficient. It is solely for describing linear relationships. There's no such thing as measuring correlation for a non-linear relationship. So we use the symbol R to represent correlation. It's got this super important property without proving it to you, that it's a number between -1 and 1. The closer we get to that positive or negative 1, the stronger we say the correlation. So this formula is pretty ugly. It needs a bunch of stuff crunched out from the ordered pairs and the individual x and y values. You'll see this worked out once by hand. Well, now, once we have a sample of data, we're producing the so-called sample correlation coefficient. Well, if we use that to describe the true population correlation coefficient, we're going to use this Greek letter. It's the lowercase Greek letter rho in the Greek alphabet. The symbol is this cursive-looking P. Please don't confuse this with proportion. Okay, so if we go to quantify relationships, and we know R is going to be between -1 and 1, this particular slide shows you some graphs with strong negative correlation. Notice near -1, some strong positive correlation near +1. More scatter here. The more the scatter, the weaker the correlation. Notice it comes out to 0.42. And a whole lot of scatter here. Notice the correlation comes out near 0. All right, so if we were describing these, they asked you to attach some adjectives to what you see. This one would simply be called nonlinear. This one would be called no linear correlation, and this one would get the adjectives perfect, positive, linear. So on the way to calculating correlation, you would have to do these 5 steps before you could get to step 6 and crunch correlation out. Those 5 steps are carried out in this example. So we have again the GDP and the CO2 emissions. If we were to write out a table with the x and y values and then add up those 2 columns, we have 2 of the quantities needed. We then must multiply every x and y in the ordered pair, add that column up, square every x, add that column up, square every y, and add that column up. If you had these 5 things in hand, you could use this correlation formula, plugging those totals into the right place. So for example, my IB students who just had to do what IB calls an internal assessment, they had a chart like this in the paper that they had to work out with this nice ugly formula. Anyway, notice that the scatter plot we made over here for GDP and CO2 emissions, we described it as positive. It looks pretty strong and positive. So now here on page 6, we have the actual correlation quantified as 0.882. As you can see on this page, that would be a lot of math. So I'm going to show you the stat shortcuts right here. Stat button. You need this list editor first. I've already inserted the x values into list 1 and the y values into list 2. So I'm going to show you this command called stat test, letter F. Stat test menu. Pretty faster to go up to letter F. Choose this option called linreg t-test. And once we do this, all of these defaults can be left as is. The x's are list 1, the y's are list 2, frequency should say 1. The letter rho, the correlation, when we do learn how to test it, we leave it on not equal to 0 in most cases. You can leave the reg equation space blank and then just go down to the calculate. Okay, now on the screen there's quite a bit. I see the down arrow here. I do need to scroll down all the way to the bottom, and I'll see the 0.882 value for correlation at the very bottom of that output screen. Okay, so here's a second example. In this second example, we have age and vocabulary, and we'd want to follow the instructions to display in a scatter plot, calculate, notice we're calculating something called the sample correlation coefficient R, and then describe and interpret it in context of the data here. So this would be a good place to just pause and go calculate this on your own. I'm going to do it as quickly as I can, but you could pause the video, go calculate it, and see that you would get the same thing as I get. All right, so the ages in the data set. Okay, and then the second list has something called vocabulary size. Oops, goofed here. Let's go fix that. That was 2100, 2600. Remember, these are ordered pairs, so you got to keep everything paired up. All right, the 3-year-old with 1100, another 5-year-old with 2000. Careful on typing those zeros. A 2-year-old with 500. 15, 25, and 2500. Okay, quick enough. Stat tests. Okay, so we've got that data in. Let's see if we can get that 0.996 correlation that I have written down here. Okay, all the way at the bottom of the output screen. So there we go, 0.996. So you've seen two examples. Notice that when I made the scatter plot, I forgot to go through those instructions. Typical x-axis, y-axis. On the x-axis, counting by ones is perfectly fine. And on the y-axis, since I see a low value is as low as 3 to as much as 2600, I just went from 0 to 3000 by 500ths. Okay, then I just plotted each ordered pair, and they kind of ended up in that kind of squished pattern right here, but clearly I can see a strong positive linear relationship. The R value confirms that, and if I interpret that, then I've just learned, of course, that as age increases, vocabulary size tends to increase along with it. Okay, next objective is to do a hypothesis test just to confirm the statistical significance of a correlation. So I'm going to run a t-test. Most often it's two-tailed, but it could be one-tailed if we wish to claim significant negative correlation. It could be right-tailed if we wish to claim significant positive correlation. Most of the time we're just looking for significant correlation and we do two-tailed. The t-test statistic is going to use the R value from the sample data as our test statistic. We're going to standardize it by dividing by this quantity. We're going to have degrees of freedom at n-2. We're going to follow a 7-step process. I forgot to adjust this a little bit, so I crossed out a few things, and I'm mostly going to focus on technology. In the examples that follow, I'll do one by hand and one with this stat shortcut. All right, so the GDP data, notice that we had just calculated 0.882. So if my poor calculator right here, if it died and I had to go calculate the significance of the linear correlation without fancy technology, I could. So I have a test of significant linear correlation. I'm not so much worried about which one's the claim, but let's assume the claim is HA, that the correlation significantly differs from 0 if we're testing for significant correlation. The alpha level, the degrees of freedom, remember it's n-2. The test statistic, if I crunch it out only knowing the R value, here's what the math looks like plugged into this equation for this T test statistic. I got 5.31. Okay, then if I don't use the new fancy stat test, if I just went to the second VAERS and did the usual p-value, looking up TCDF, I got 5.31. I need the tail area, so 5.31 to 10,000. Put in the degrees of freedom. That's 100,000. It doesn't matter. Degrees of freedom 8. Enter. And then I'd have to remember I'm doing a two-sided test, so I hit times 2. And there's my 7.19 whatever, so 7.20 e minus 4 is on my screen, and that I know would be 0.0072. So since that is less than 0.05, we reject HO with a final conclusion that there is enough evidence to support the claim that there is significant correlation between CO2 emissions and GDP. So second example with braking distance, we have weights of 8 vehicles in this data set and the variabilities in their braking distances when stopping on a wet surface. At alpha equals 0.05, is there enough evidence to conclude significant linear correlation? So since it doesn't say significant positive or significant negative, we're asked to do a two-sided test. Alpha is 0.05, there's 8 cars, so there's 6 degrees of freedom. These two steps 4 and 5 would just be found on the output screen after creating the data set. I'm wary that this video is getting kind of long, but if I was doing it, it's in the stat test menu, letter F, okay? Just like the correlation steps, calculate, this is the t-test statistic of 5.61 from the, a t-test from what data? That would be the vocabulary data that's in there. My bad. So anyway, these two numbers right here at the top would be what you grab off the output screen, the t and the p-value. Put this data in list 1 and list 2. You'd read this t and this p-value off your calculator screen. And of course, we got another low p-value, so we're going to reject HO with a conclusion that there's enough evidence to support the claim of significant linear correlation. Okay, and then final little objective number 4, to distinguish between correlation and causation, we have to beware. It's a buyer beware statement. The fact that two variables are strongly correlated does not in itself imply cause and effect relationship. If there is significant correlation between variables, the reason we don't have cause and effect is because oftentimes when you ask yourself directly if X causes Y, there's a no answer to that. Because sometimes it's really that Y that causes X, it's the reverse. Sometimes, and number 3 is the most important one, that the relationship between the variables is really caused by a third variable or a combination of other variables. In an example of CO2 emissions and GDP, there could be lots of other things other than a country's GDP causing its CO2 emissions. So pollution could be caused by many things like the strictness of the laws, the number of power plants the country has, the amount of industry, all kinds of things. How waste is disposed, etc. And then finally, the relationship could just be a coincidence. My favorite coincidence example is to say, what if I see a significant correlation between drowning and beer sales? Well, the coincidence could just be when it's hot outside, people drink more beer and people swim more often. So naturally, beer sales go up and drownings go up, but not because the beer caused the drownings. Alrighty, so that's the end of all of section 9.1 through page 10 in the note packet.